Hi all. For this module, we're going to be discussing the single cycle data path. So to start, let's review what a register does. So what a register does is it passes the data from data in into data out and remembers the data even if data in changes. So for example, data in for this one started at OXAB. After the clock pulse told it to load data in into data out, OXAB appears in data out and remains there despite data in changing. And then once once the next clock pulse comes in, it takes the new value of data in and puts it into data out again, which is OXF1. Now, an important function for the register that we have is the enabling function for the single cycle data path. So here, if you have a write enable input onto the register, what happens is that it only takes data in and puts it into data out if and only if write enable is 1 at the time. So in contrast with this first happening, OXF1 is not loaded into data out. So OXF1 is not loaded into data out because at the time that the positive clock edge pulse hits the register, the write enable is already 0, so it won't. It remains. The data out remains the same if write enable is 0. So that's going to be important for our construction of the single cycle data path. So the single cycle data path is basically the computer. It's already a processor. So how I think personally about a processor is that you have states that is determined by the internal registers or the internal memory files of the computer, and then you have an instruction. So the instruction is the input, and the instruction forces the computer from one state into another state, and then yet again into more states once you read more instructions. So for us to execute instructions, we have to design the processor in order to be able to do the following. First, it must be able to fetch an instruction from memory. And next, with that instruction, we need to be able to know what we need to do. This is called the decode step, or we determine what the instruction does. For 3, we fetch the operands of the instruction from the internal memory or from the register file. And then the register file is a set of registers that determine the state of the computer. We will see that later. And then we perform a specified operation on the operands, like add, sub, or, and AND. And then lastly, we store the result back, maybe onto a register or maybe onto a memory file. But fact remains, we need to store the result after we perform the operation on it. If we don't store the result, then we might as well not have performed the instruction at all. So for us to fetch instructions, this is how we do it. So this was step 1. So instructions are stored in a special memory called the instruction memory. And succeeding instructions are addressed sequentially. So what do we mean by that? Say we had the first instruction in OX400, the instruction following that will be in the next address after it, or rather, four bytes after it will be the next instruction. And the succeeding, so these two are succeeding instructions. These are put into the processor sequentially. And in each cycle, the address is incremented to point to the next instruction. So basically, every cycle, we add 4 to the program counter, and we put that current address inside the program counter into read address, for which the instruction comes out. So say for example, we have add here. and this would be OX 400, and as follows. So the program counter also stores the address of the current instruction for a single clock cycle. So in the next clock cycle, only for a single clock cycle. So for the next clock cycle, we will add 4 to the program counter. And so we're going to have OX 404 now here. And so the instruction coming out will now be sub after the first clock cycle. The program counter, if it wasn't evident, is a register. So you can see here there's an input for the clock and it has an output. So it is a register and it must be incremented every clock cycle. Okay, so how do we actually do this? Since this is a register and this is a memory file, which you can think of because it's ideal as a big register, we have the program counter, and then we feed it to both the read address of the instruction memory and into an adder whose other input is OX4. So um, so since the adder's input is 4, then the output of the adder will be PC plus 4, and so we feed PC plus 4 into PC every clock cycle. And this will always, the output of the instruction memory will always be the current instruction because PC is being fed into the read address. So that's it for fetching instructions. To fetch the operands for an instruction, we have something called the register file. So I mentioned this earlier. The register file is a collection of registers. So we have a bunch of inputs to the register file. We have a write enable. So write enable, basically, it was what we talked about earlier. It enables writes to be done onto the register, onto all the registers inside the register file. And we have read register 1, read register 2, write register, and write data. So what happens here is that whenever you read something from read register 1, say you want to read register number 4, the contents of register number 4 comes out from read data 1. When you put in, say, register 3 inside the read register 2, the contents of register 3 comes out from read data 2. This is pointer 3, pointer 4. And internally, this is what happens. So you have, say, for example, we just have read register 1 in this example, but internally, you have read register 1 coming into a MUX, and then whatever this is, say, for example, this was 0, it will let through 0 if it was 0 into read data 1, which means that read data 1 will contain whatever R0 contains at the moment. Write enable decodes. So basically, here, the write register basically chooses which register we want to write into, and write data determines what data we write into the registers. So you can see here, the write data is just broadcasted onto all the registers. So even here, say for example, this is register 2. So that's broadcasted onto all the registers. And how do we choose which register to write onto? We use the enable of the registers. So this top input is the enable of the register, and we put that into a decoder. So say for example, we wanted to write into register 2, then the decoder will choose register 2 to enable. So this will be 1, but that's if and only if write enable is 1 for everything. If, say, write enable was 0, then all the outputs of this decoder will be 0 because you don't want to write into anything. Okay. So with that information, let's implement add and sub. So here we have the instruction coming out of the instruction memory. This is the instruction decoding. We've discussed this before. So the opcode determines the instruction, and we have RS, RT, and RD. RD stands for the destination register, so we put that into the right register of the right register input of the register file. The RS and RT are each of the two operands, so we put those into each of the read register inputs of the register file, so that we get the RS source operand from read data 1 and the RT source operand from read data 2. So that's so now that we have the operands, we need to operate with those. Remember that this one is RS and this one is RT, or rather the data inside RS and the data inside RT. We put that into the arithmetic and logic unit. So the ALU basically does anything to the two inputs that we specify it to do, at least that we've decided to be able to do. So we need to specify a ALU operation or ALU op control signal into the ALU to select the appropriate operation for it. And then the result will come out, and then we put that back into the right data of the register file so that we could write it into the RD destination. And of course, we write enable if we wanted to write it back. So here, the ALU also has a special output, which is the control flags. So this may not just be 0 depending on your data path, but we have it. We just have it as 0 for now. This is, for example, if you want to branch if not equal. So if not equal, you're just going to specify, say, sub as the ALU operation, and say if RS minus RT, if that was equal to 0, then this thing would be 1. That is, this would imply that RS equals RT, and so we could use this flag in order to do a branch if not equal. But that's a topic for later. So this complete single cycle data path supports the R-type arithmetic instructions. That is, all the instructions that we can specify with just ALU op, and that writes back to the register file. So here we have the fetch stage. So PC plus 4 goes into PC, and then we put PC into read address. So that's this is PC, and this is PC plus 4. PC goes into read address, and then the instruction comes out. This is the current instruction. We read the destination register and the two operand registers. The two operand registers come out here, and then that goes into the ALU. The ALU op is fed into the ALU. Of course, we have to feed the instruction into the control unit for the control unit to find out what ALU op and write enable should be. But in this case, ALU op has to be, depending on the instruction, add, sub, and, or, and the result comes out of the ALU, goes all the way back here into the right data port. And so we put write enable as 1 here because we want to write the ALU result into the destination register. So that's the entire cycle for the R-type arithmetic instructions. For this control unit, it's quite simple. If we only have to, if we have the control unit to support only the R-type arithmetic instructions, write enable is always 1 because we never don't want to put write enable for these R-type arithmetic instructions, else we wouldn't be doing anything. ALU op depends on func. So if you remember, func determines for R-type arithmetic instructions if it's add, sub, and or and and. So that's why ALU op depends on func, and ALU op is one of these or more depending on what we have. There's sometimes reverse subtract and stuff like that. So our control unit basically has write enable hard-coded to 1, and then ALU op fed from func, and then func1 because here in this case we have just add and subtract, right? We only support add and subtract. So if it's add and subtract, then this one we only have to look at the first the least significant bit, which is funct 0. So we put that here, and if funct 0 and funct 1, rather the first two bits, if these are both 0 or these are both 1, then allop is 0 if uh, add, 1 if sub. So our ALU in this case only has two operations that it's able to do, either add or sub, and we have a 1-bit allop control signal. So a question to think about: how do we implement the control unit if we consider undefined instructions as no operations? So NOP is basically if we don't understand the opcode, for example, if it's not a instruction that we were supposed to be able to support, or that is not part of the ISA, then we call those instructions no operation. That means that we're not supposed to do anything when we read it. And so um, what we do when we implement the control unit like that is actually we just change the write enable. So the write enable used to be that it's always one, right? But if, for example, if it's a no op, then so if it's a NOP, say this is some sort of decoding function that we know it's not part of the known instructions that we have. So if this is 1, then we turn it 0, and then we can put this into an AND, so that if this is 0, then this is 0. So this would be write enable instead. So whenever it's a NOP instruction, then we put the write enable to 0, and that makes it so that nothing is done by the instruction. Even though we've calculated something from the ALU, we're not going to write it back, so we might as well not have done anything for the instruction. Okay,